Okay, I'm going to record this meeting now. And going to the full screen mode now. Wait a minute. Oh, there it is. Okay, welcome back, guys. So I'm really happy that I figured this out so you can actually see clear things, see things clearly from now on. Of course, we only have a few more classes, but yeah. Anyway, I should have figured this out much earlier. So how are you doing today? I hope everybody's doing fine. And so today, just to give you a quick recap of what we have done last time. So we looked at the D flip-flop, right? And before I proceed, because I'm putting this in the full screen mode, it's very difficult for me to look at your chat messages now because I'm just looking at the whole screen of video. I'm not looking at this. I don't have the pods anymore, unfortunately. But regardless, I will be able to intermittently check those messages anyway. Okay. Now, just to give a quick recap of what we have done in the last class, we looked at the D flip-flop and some applications of D flip-flop, right? So we've looked at the register. We have the parallel load register, and we have looked at how these registers are interfaced with the data bus, and also we looked at another alternate way of implementing registers. We also have the serial version of the registers called the shift registers, right? And and towards the end of the class, we also looked at what is called the universal shift register, a register that can perform all of these operations: the parallel load, parallel read operation, serial or shift right, shift left operations, um, and of course memory operations, right? So the universal shift register is something that could actually perform all of these operations. Okay, so that's good. Now let's move on. Again, before we actually move on, I just want to remind you what the characteristic table for a D flip-flop is. Okay, now so for an edge triggered D flip-flop, the characteristic table would be something like D. That's the D input, and then you have, again, I represent QT plus 1, which indicates that, which basically means that I'm applying some input on the inactive edge of the clock cycle, and I'm looking at once the flip-flop is triggered. Okay, now when the flip-flop is triggered, when we have the active edge with the flip-flop is triggered, that means the output responds to the input, right? The output responds to the input. That's when we call that the flip-flop is triggered, right? So in this case, if I put 0 on my D input on the inactive edge, okay, and I will wait until the next active edge occurs, and upon the next active edge, my Q follows D. That's how the flip-flop behaves, right? And likewise, if I put a 1, and then in the next active edge, my QT plus 1 becomes 1. Okay, and so you can see that I don't really have another state called the memory state for a D flip-flop here, the way I've written this. Now, so how would we obtain the memory state? Again, we addressed this in the last class through the use of what is called the load enable input. So in addition to a D flip-flop, we also use a multiplexer. Okay, and so by using the multiplexer, we have this. We can constitute a state called the memory state, have an additional input, load enable input, to that entire system, so that I can place some values on my flip-flop, which is part of a larger register, depending on what I apply on my load enable input. Okay, the reason why we need this is because you have this common data bus, right? Again, the bunch of lines, right? The data lines. These are connected to multiple registers, and I should be able to pick and choose the register I want to store that information in at a given instant of time. This load enable allows me to do that. And in the last class, we also looked at the scheme to produce addressing. Okay, so if I have 4 registers at a given time, then I can have a 2-bit address, a unique address for each register, right? And then when I apply that address, basically I'm selecting that particular register, and then I enable the load enable signal on that particular register, and the data is stored in that particular register. So that's how it works. Okay, among multiple things, how do I pick and choose a single register? And likewise, you can also extrapolate the same idea to the memory. Okay, to external memory. Again, you have memory locations where each location can store some information. Each memory location will have its own address, a unique address. Okay, and in the last class we kind of looked at how this addressing scheme works. Okay, and by having the unique address, I can specify in which memory location I can store information in, or I can retrieve information from. That's the idea. Again, my goal here is to connect you, at least at the intuitive level, to see how things actually operate at the hardware level. Okay. All right. So that's the characteristic table for the D flip-flop. Now let's examine the D flip-flop, and I would like to modify this a little bit and see what kind of additional functionalities we can get from that modification. Okay, so I'll start with the D flip-flop. Again, I have two outputs, Q and Q prime. Again, from now on, of course, I'm working with edge triggered flip-flops. So that's my clock applied. Again, in this case, again, that's a negative edge triggered flip-flop. Okay, and I would like to modify this a little bit. So what I'm going to do is I'm going to have an OR gate, and you will see why I've done this. I have two. Basically, what I'm doing here is coming up with a combinational circuit. Okay, in addition to this, in addition to this D flip flop. Okay, simple combinational circuit. It's again, so I have two gates, two AND gates. Let me call this input J. Okay, and the other input, again, I have the feedback going from Q prime. Okay, and then of course the output of this goes to the OR gate. Then I have another input K. Of course, I'm inverting the input here. That's signified by that bubble. And then as the other input, I take Q as the other input. There you go. And of course, the output of this goes back here. And this goes to here. And I would like to analyze the circuit now. Okay. So I have this circuit. I've just modified the D flip-flop, not modified the D flip-flop itself. I've just added a combinational block in front of the D flip-flop. Now I have two inputs, J and K. Okay. And I would like to analyze how the circuit behaves now. So what do I do? Now again, I go with the modular approach. I know how this module works. For a given input here, D, I know how Q and Q prime behaves, right? So I know that information. So now I have two additional inputs. So the way I will do this is I would come up with a table, J, K. My intermediate input becomes D, which is here, right? The output of this is nothing but my D input here. So I'm going to call that D, and then Q of t plus 1. Let me call that t plus 1. Again, to represent that, if I apply an input, then what is happening to that output, how the output gets triggered, how the output gets modified on the next active edge. Okay. All right. So now let me look at all possible combinations between J and K, because these are the independent inputs, right? I can apply any input here, J and K. These are the independent inputs. D is a dependent input here because D depends on what values you apply on J and K, right? All right, so let's do that. JK 0, 0, 0, 1, 1, 0, 1, 1. Okay. Now, because D depends on J and K, right? Because D is nothing but the output of this gate. Now, so what is D anyway? So if I call this D, what is D in terms of, because it's a simple combinational circuit, right? So D is nothing but J times Q prime or J and Q prime, J and Q prime, right, from this AND gate plus or K prime and Q. Right? So now all I have to do to get what my D is plug in the values of J and K. These are the values of J and K. Plug in those values to get D. So if my J and K are both zeros, what do I get for D? My J and K are both zeros. Again, J is 0, right? So my D will be J is 0, so that takes my J and Q prime to 0. Or K is 0, K prime is 1, so that leaves me with Q. Okay. So if I apply J and K to be both 0, 0, my D becomes Q of T. Okay. So I'm basically applying, I'm recirculating Q back to the D through this feedback mechanism. So at my input, D input, I'm applying Q of T. So in the next active edge, my Qt plus 1 remains as Q of T. It doesn't change. So again, that constitutes your memory, right? Okay. I hope that makes sense. And likewise, I'm going to do for the rest of the columns in the table and the rows in the table. All right. I will do exactly the same thing for the next one. If I apply a 0, 1 on my J and K inputs, what happens to D? I'm applying a 0, 1. That means J is 0. That takes J times Q prime to 0. K is 1. So that takes K prime to 0. So that brings everything to 0. So that basically 0. In other words, when I apply J and K to be 0, 1, then my D input here is 0. I'm applying a 0 at the D input. And in the next active edge, my output, because that's a D flip-flop, the output follows the input. The output is basically becomes 0. That's the reset state. Okay. Now, what about the third row? If I apply J as 1, J is 1, that's 1 times Q prime, that's Q prime. Or my K is 0, K prime is 1 plus Q, that's 1 times Q is Q. Again, going back to your Boolean identities, we see that Q plus Q prime is nothing but 1. Right? X plus X prime is always 1. A variable ORed with its complement is always 1. So that becomes 1. In other words, I'm applying a 1 on my D input. And in the next active edge of the clock, my Q follows D and Qt plus 1 becomes 1. So that's your set state. Finally, we have J and K both 1s. When I do that, what am I going to get? J is 1, that's basically Q prime. I'm sorry. Yeah, that's Q prime. Plus K is 1, that means K prime is 0. That brings everything to 0. So, and I end up with Q prime. In other words, when I apply J and K both 1s, what I'm applying to D is Q prime of T, the complement of the previous of Q. Okay. So in the next active edge, what do I get? And the next active edge, once my flip-flop is triggered, I end up with Q prime of T. So it was Q of T at the inactive edge. In the next active edge, it became Q prime of T. In other words, it got the output Q got complemented. Does it make sense? So that's the characteristic table we got for this new type of arrangement using the D flip-flop and a bunch of combinational gates. And we call this the JK flip-flop. So in addition to some states that we add for the D flip-flop, we have new additional states for the JK flip-flop. Particularly, we've already seen these states. For the SR latch or SR flip-flop, we've already seen that. We haven't seen this one. Instead of, remember, for the SR flip-flop, my S and R both ones gave us some forbidden state, the state that we wanted to avoid, right? On the other hand, here we have a very definite state. It's a determinate state, and we can actually use it to our advantage. So in this particular state, because my output gets toggled, when my J and K are both ones, my output gets toggled, right, with every active edge. If I just keep J and K to be 1, my output is going to get toggled with every active edge. Okay, and that's why we call this the toggle state. Toggle as in it gets complemented. So with J and K equal to 1, that gives me what is called this toggle state. Okay, now, so that's well and good, but let me represent that in the form of a timing diagram to make it to make it more clear. Timing diagrams are very handy to understand the circuits, digital circuits. We've already seen that. So let's actually look at the timing diagram for a JK flip-flop where my J and K inputs. So now I can actually represent the JK flip-flop instead of having that entire diagram. It's a new type of flip-flop we'll be using very often. So basically I will represent this with its own symbolic diagram. In this case, we have two inputs J and K, two outputs Q and Q prime, and of course the enable input. Again, that's in this case, again, you can have a positive edge triggered flip-flop or a rising edge triggered flip-flop or a negative edge triggered flip-flop like this. In this case, I have just drawn a negative edge triggered flip-flop. Okay, so that's where I apply the clock. Now in this case, I have two inputs for this flip-flop, J and K. So that's the symbolic representation for a JK flip-flop. Okay, and now what I'm trying to do is I'm trying to basically apply. I'm trying to apply J and K both once. Okay, and I'm trying to observe what Q becomes as a function of my clock. Okay. All right, so let's do that. Let me see in the meantime if you had any messages there. Okay, yes, let me get back now. All right. Why that's frozen? Okay. Let's see why this thing is frozen. Are you guys able to see me still? For me, my screen is frozen for whatever reason. Frozen, right? Okay. Full screen mode. Okay. All right. So we're back here. So I'm going to draw the timing diagram now. All right. So again, I start with the clock, the master clock, and yeah, just a master clock again because my inputs. I'm tying my J and K to be 1. So basically, my J and K are both 1. That means with every active edge, my output gets toggled. Okay. So let's do that. So here's my master clock. That's a negative edge triggered flip-flop, as you can see there. Let me actually do it here so we have enough room. All right. So I start with the clock, and then yeah. Okay. So my clock is the one that determines the timing. So here it is, and I will identify what my active edges are. Okay, so that's my clock. Again, this is a negative edge triggered flip-flop, so these are my active edges where my flip-flop outputs get triggered by the inputs. All right, let's assume that Q was 0 to start with. That means that's my clock, 0 and 1 level. That's the clock signal applied to that flip-flop. So I'm assuming that at time t equal to 0 here, my Q was 0 to start with. Okay, so it's 0. Now, this is the next active edge, right? This is the next active edge. Now, what happens at the next active edge? My Q becomes Q prime, right? At the next active edge, my Q becomes Q prime. In other words, if I 0 to start with, then the next active edge, it toggles. So 0 becomes 1, and it remains 1 until when? Until the next active edge. This is the next active edge. And the next active edge, my Q becomes Q prime. Of course, it toggles again. The previous Q becomes Q prime, and it keeps doing that. At every new active edge, my output toggles in a very controllable way, right? Because it basically follows the clock. With respect to the clock, with respect to the active edges of the clock, my output toggles. And that's it. So now I have obtained the state, the toggle state, which is represented like that for the JK flip-flop. When I place J and K inputs tied at 1, apply the clock, my output toggles every clock cycle. Every new active edge, my output becomes the opposite, or the complement of the previous output. Okay. So what are the uses of this? What kind of use can we have for this? Before we do that, what can you say about the frequency of this new signal? This is Q, by the way. I've not represented J and K because they are anyway just 1, constantly at 1. So I don't really have to show that. So I just directly showed Q. Now, what can you say if I have a clock frequency of Fc in this case? What can you say about the frequency for Q? Because again, Q is also a signal. It's also a square wave signal. And you'll see that the frequency of Q is half of the frequency of the clock, right? The frequency of Q is now half Fc over 2 of the frequency of the clock. Okay, so I can divide the frequency. It halves the frequency of the master clock. But again, what are the applications of this? What can we actually do with this? What can we gain from this? Right. Now let's examine this circuit, and then you will see what this actually does. Again, I'm going to use I'm going to focus on the toggle state for now. All right. So let's examine this simple circuit here. So I'm using, let's say, 4 JK flip-flops. That's 1. That's 2. That's 3. And that's 4. Okay. So this, let me call this JA. No, let me call this JD, KD, QD, Q prime D. This will be JC, KC, QC. This will be JB, KB. This will be JA, KA. And I'm going to configure them all in the toggle state. That means I have to make sure that my J and K inputs are all tied together, and these are applied at 1. Okay. I'm applying constant voltage of not one volt, but one, the level 1. Okay, it could be 5 volts. Okay, and so these are the clocks. These are the enable inputs. So what I'm going to do with the enable inputs is that I will apply the master clock to the first flip-flop. That's the master clock, and see what happens now. And then I would, for the clock for the second flip-flop, I will take the output of the first flip-flop, apply it as an input to the enable input of the second flip-flop. Likewise, I apply QC as a clock to the third flip-flop, QB as a clock to the fourth flip-flop. Okay, and then I will try to plot this out in the form of a timing diagram. I would like to see what kind of a function it does. Okay. So this is what I have. Again, we have, if you really look at this, what I have analyzed here is QD, right? I can basically call this QD, right? QD, because I'm applying a clock directly to this flip-flop, and I'm trying to monitor QD, and of course my J and K are both tied to 1. That means I'm configuring this flip-flop in the toggle state, and I'm monitoring QD as a function of clock. And this is exactly what I would get for this particular flip-flop. Now what about QC? If I want to plot QC, now for QC, my QD is the clock signal to QC, right? My QD is what is being applied as the clock as the enable input, as a signal to the enable input of my QC flip-flop. So basically this is functioning as a clock to my QC. Okay. So if I want to plot what QC would be, right? First of all, I need to identify what the active edges are. Again, these are all negative edge triggered flip-flops. So my active edges are going to be, so this is an active edge. Here's another active edge. That's the active edge for the QC flip-flop, and so on. If I want to plot QC, that would be something like this. All right. So I'm going to plot QC. Again, my QC, the JC flip-flop, JK flip-flop, or JC KC flip-flop is configured in a toggle state. So if I assume 0 to be the initial state of that flip-flop, it toggles at every active edge of this clock, the QD clock, because that is what is being applied to QC or JC and KC. So this is my active edge. My QC toggles at every active edge. There you go. All right. So that's what I get for QC. Okay. Because my QD is the clock for JC flip-flop. Now, if I compare the frequency of this signal that I obtained from QC with respect to the clock, you'll see that the frequency is actually this is half of the frequency of FC by 2. That means if I compare it with the master clock, which is FC, the frequency of this signal is going to be FC over 4. So I've divided the frequency by 4. Okay. Now let's do QB. Same discussion. The only difference here is I'm applying QC, the output of QC, as a clock to the JB flip-flop. Right. So in this case, my QC becomes the clock, So those are my active edges. So I identify my active edges because that's a negative edge trigger flip-flop. Again, I assume QB to be 0 to start with. So if I want to plot this, this is what I would get. So QB was, let's say, assuming to be 0 to start with. So QB toggles at every active edge, right? So my QB would be to toggle at this particular active edge, becomes 1. It remains 1 until the next active edge here, and then it basically gets complemented.
Dr. K.
That's QB. Again, going by the same logic, the frequency here is FC over 8, because the frequency is
Dr. K, we can't see you.
oh, what happened? Okay. All right. So QB, the frequency is FC over 8. I can do exactly the same thing for JA, right? In this case, my QB is the clock to JA. So these are my active edges for my JA flip-flop. So if I want to plot my A or QA, all right, my QA, let's assume that QA was also 0 to start with. What do I get? My QA is 0 until the next active edge, which happens here. So that's 0. And then I get a signal here. And it remains 1 until QB goes down, until the next active edge on QB as well. Right? So that's my QA. All right. Now, so that's all good. Let me actually take any questions you may have. Any questions so far? Does it all make sense? Okay, very good. Let me get back to the full screen mode. All right. So now, so what do we have here? Right. Number one, I have this frequency. So with this circuit, I'm able to divide the frequency. I can actually get signals that are of different frequencies with respect to the master clock. So I can divide the frequency, right? Now, what could be a possible application of that? Frequency division. Where can we use it? Now in your computers, right? Your computers are, again, your clock speeds are in the gigahertz range, right? The latest computers that you're working with, these are in the gigahertz range, the clock speeds. And how many flip-flops like these do you need so that you can actually divide the frequencies? Because again, the clock on your computer, the clock that actually shows the time, you have the hours, minutes, seconds, right? You have to basically divide this with respect to, again, that functions with respect to the master clock. So basically you're dividing the clock's frequency so that you're actually getting the hours, minutes, and seconds on your computer. Okay. Now that's one application, of course. Now what are the other applications? If I notice, if I do this, if I just tabulate what I'm having with respect to different clock cycles, all right. So let me call this the clock input, or the number of clock cycles elapsed. And then if I notice what my QA, QB, QC, QD values are with respect to this clock, okay. So on the 0th clock pulse, that means on the 0th clock pulse here, you'll see that all the values of my QA through QC or QD are all zeros, right? On the 0th clock pulse, this is the first clock pulse. Or this is the first clock edge. This is the first active edge, right? So on the 0th clock edge, you'll see that all of these values are zeros. So I can write these to be zeros. Right? on the first active edge, or I can call it the first clock pulse, which is happening here, right? My QD is 1, everything else still remains 0. Right? QD is a 1, everything else still remains 0. On the second active edge, which happens here, second, my QD becomes 0, because obviously it's toggling, right? With every active edge, my QD is toggling. What about QC? My QC becomes 1, right? My QC is becoming 1. And then QB and QA are zeros. On the third active edge, so that's the first, second, third, fourth, fifth, sixth, seventh, 8, 9, and so on. Okay. On the third active edge, which happens here, my QD goes from 0 to 1. So my QD is being recorded as a 1. My QC still is 1, right? My QC, the value of on QC is still 1. Okay. QB and QA are still zeros. On the fourth active edge, which is here, QD is again toggling, that goes to 0. QC is toggled, that goes to 0. QB is toggled, that means it was 0 before, it became 1, that becomes 1, and that's still 0. On the fifth clock pulse, which is here, QD again toggling, that becomes 1. This is the fifth clock pulse. QC is 0, QB remains 1. That's 0. On the sixth, QD is toggling, that goes from 1 to 0. QC toggles as well, that goes to 0 to 1. QB still remains 1, and QA is still 0. On the seventh, QD is 1, QC is 1, QB is 1, that's it. On the eighth clock pulse, which is here, again QD goes from 1 to 0, QC is going from 1 to 0, QB is going from 1 to 0, QA is going from 0 to 1, and so on. Okay, so this is what I have for this particular case. So what am I really doing here by monitoring my outputs QA through QD? What is it doing? If you look at the values of the binary values here with respect to the number of clock pulses elapsed, it's basically counting the number of clock pulses, right? 0, 1, 2, 3, 4, and so on, right? In other words, it's functioning as a counter. As a counter that can count the clock pulses. Why is it important? Because, as I mentioned before, again in a system, when you're working with a complex digital system that consists of multiple modules, multiple subsystems, each of the subsystems are interconnected, right? And then some subsystems may take more number of clock cycles to execute an operation compared to other subsystems, right? Depending on the complexity of the subsystem, some subsystems may take more number of clock cycles than the other. So if I want to interface them, if I want to synchronize these operations, I have to provide them with the clock with proper timing signals. These counters allow you to create these timing signals so that, for example, here, right? Now this particular signal here is on for how many clock cycles? This particular signal is on for 1, 2, 3, and 4. So that particular signal is on for 4 clock cycles. So I can use this as a timing signal to indicate that this, let's say a subsystem takes 4 clock cycles to execute an instruction, and then after the instruction is executed, I want to make that system or subsystem inactive. Okay, So I can provide this as a timing signal, the QB as a timing signal, so that it's basically active for 4 clock cycles, and then after the four clock cycles elapse, that becomes inactive. Okay. So this way I can actually provide the timing signal. Again, this is just a simple example of a counter. You have a large number of a number of different counters that are available that can serve this purpose. Again, providing different kinds of timing signals. Okay. All right. So that's a counter. And how many counts do I have? With 4, how many unique counts? Right. I have 4 flip flops here, and I'm able to get how many counts? From 0. With 4 flip flops, I'm basically able to get a count all the way from 0 to 15. Right. Although I have not shown them all, you can easily do that. I'm getting a count from 0 to 15, or I'm basically getting 16 unique counts, 0 through 15. So total number of counts are 16. So this is also called a modulo 16 counter. Modulo 16 as in how many, it basically specifies how many unique counts do I get from this particular counter. For example, if I just use 3 of these flip-flops here, I would have obtained a counter, a modulo 8 counter, right? Because that goes from 0 to 8, 0 to 7. Okay. Or I can simply say, in terms of if n is the number of flip-flops I have, then that if I construct a counter with n flip-flops, then that would give me what is called a modulo 2 power n counter, because I can basically get 2 power n unique counts using n flip-flops in a counter configuration in this way. So that's going to be a modulo 2 power n counter. Okay. All right. Now, and because of the way these flip-flops, this counter is constructed, right? As you can see here, the clock of one output of the flip-flop goes, the output of one of the flip-flop goes as the input, as the clock input to the next flip-flop. So in other words, this clock signal is being rippled through indirectly through this configuration, right? The effect of clock is felt through this configuration, right? So this is also so that's why this particular flip-flop is also called the ripple counter. This is a counter, and it has a name which is called the ripple counter. This particular counter. So as you can see here, I'm able to utilize the toggle state for my advantage. I can actually obtain these kind of timing signals. I can generate these kind of timing signals from these configurations. I hope that makes sense. All right. Now, so that's well and good. Now, do you see a problem with this kind of a counter? Any issues? Of course, it works. Now, any potential issues that you can think about, especially when we want to increase the number of flip-flops in my counter? What could be happening? Any issues here that you can notice? So how are we doing on time? Okay, that's good. Yeah. You can see, again, these are circuits. These are active circuits. These are switches, these gates, and they have their own switching delays, right? It's small, but it is there. All right. Now the switching delays will be more apparent when I increase the number of flip-flops in my design. Okay, that's good. So let's see what happens through this. Again, we can visualize that the problem using the timing diagram. So now I can work with everything with respect to the timing diagram. Now, what I'm trying to get to is there any fundamental limitation? Now, with respect to how many flip-flops I can use in my design before I can, before I should stop. Okay. Now, we didn't have this issue when we discussed the adder slash subtractor circuit, the cascaded adder slash subtractor circuit, because there, of course, we had this timing delay and problems like associated with that. But if I wait long enough time, then the output would still settle down to the right value. But here, that's not going to be the case. And this is why it's not going to be the case. So this here I have to have a constraint placed on my design. Okay, and let's see what the constraint is. So this is a ripple counter, and there are some disadvantages associated with this design. One of the disadvantages, again, one of the direct disadvantages, when you're, and this is again a rule of thumb, if you will, when you're designing a digital system, like a computer architecture, when you, one rule of thumb is you don't want to put anything in the path of the clock. You don't want to modify the path of the clock itself. The clock should be a synchronizing signal that is applied to all the units at the same time without adding additional additional circuits in the path of the clock. So ideally here, what we should have done, or we should have come up with a better design where this clock, instead of being applied in this way, because again, you're not directly applying clock, this master clock, to this flip-flop, to this flip-flop, and to this flip-flop, right? You're only applying the master clock to this flip-flop. Now for the rest of the flip-flops, you're really, the output of the previous stage goes as the clock signal. So in other words, you're kind of creating some kind of circuitry in the path of the clock before you're applying it to the additional to the other units here. Okay, so that's not a very good way of designing systems. Okay, all right. So what I'm saying is, now this particular flip-flop, every flip-flop will have its own timing delay. That means when I apply the clock and the inputs, and when the flip-flop gets triggered, there is slight delay between uh, the the occurrence of the active edge and the switching activity of the flip-flop. In other words, if I want to redraw it, what is really happening here is, even though I've shown it to be exactly there, what really happens is there is slight timing delay. So here, this is an idealized situation where the signal, the toggling of QD is exactly matched with the active edge. In reality, because you have a slight delay for the conduction of these signals through the flip-flop, my flip-flop is going to switch at a after a slight timing delay, something like this. So this is going to be my actual. It's going to be small for a single flip-flop. It's going to be very small. Again, the same thing happens here. This is the next active edge. It is supposed to switch exactly coinciding with this active edge, but of course, because of the timing delay, it's going to switch after a slight delay, which we call the timing delay of this flip-flop. And let's say this is my what is called the TP, the timing, the delay for the propagation delay, if you will, of the signal. Are you able to see that? Okay. So if I am using a single flip-flop, it's barely noticeable. You won't even notice it. It's so small, right? Now, but what happens here? Let's assume that the timing delay is more or less uniform across all the flip-flops. Let's say each of the flip-flop has a timing delay of TP. Okay. So for the second flip-flop here, QC, same thing happens, right? It's supposed to be, because this is the next active edge. Yes. QC was supposed to switch corresponding to this particular active edge of the master clock, but because this is the active edge, this is the counter, this is the clock applied to my JC flip-flop. So now this is the active edge. Okay. So instead of switching here, it's going to switch. Instead of switching here, because it has its own timing delay, because this is supposed to switch here, but because of the timing delay, it's going to switch here. And likewise, same thing here. If this was supposed to switch here, switch down here, but but because of the timing delay, it's switching after a slight timing delay here. So this is the active edge for this particular flip-flop. Instead of switching here, it's going to switch with its own timing delay. Now, what happens to the timing delay here? Now I have an initial timing delay with respect to the master clock. I have TP here because of this delay of switching in the first flip-flop, and TP added because of the delay of the switching of this own flip-flop. So now I have 2 times TP added to the delay in switching. And this delay is going to get propagated now. Same thing here. For the QB, this is going to switch after a delay of 3 times TP. Instead of switching here, it's going to switch after a delay of 3 times TP. And this delay is going to increase as the number of stages are increased, and eventually reaching a stage where my n times TP for the n, let's say I have n flip-flops here, n times TP becomes equal to the clock period itself. And that is not acceptable because now I'm going to get some intermediate wrong counts, which is not acceptable, right? When n times TP, that means either I increase the clock period, in which case I'm basically slowing down my system, which is not advisable, or I limit myself to the using few number of flip-flops so that my n times TP is always less than the clock period. Okay, that way I will always get the right count. But so I have to live with this constraint when I'm working with ripple counters. So this constraint exists. Okay, so as you can see here, this timing delay basically gets propagated, becoming larger and larger as more number of stages are added, and once this exceeds the clock period, then I'll start getting wrong counts that can mess up my entire system, right? Mess up your clock, for example. Okay, so with that, we have identified, again, we wanted to see what are the advantages of a counters, how do we build a simple counter using or exploiting the toggle state of a JK flip-flop, okay? And so that's your ripple counter. And we have also seen that we have, of course, problems associated with ripple counters. So we have to see what we can do to avoid those problems. Okay, so let's look at an alternate design. In this case, this is called a synchronous counter. Synchronous because my master clock is applied to each of my flip-flops. Okay, instead of having it rippled through, my master clock is applied. So each and every flip-flop is basically synchronized with the master clock, so we don't have this problem of propagation delays anymore. Okay, and let's see the design. So let's examine a synchronous counter design. But before that, I hope it makes sense. Any questions, comments so far? All good? Okay, very good. So let me look at the design, and this time I would like you, okay, let's see how we can do this. Usually I would like the students to actually come up with the design, or at least provide me with the input. So let's see if we can do this. A synchronous counter. So as you can see here, even when we're designing the sequential circuits, of course we are using the flip-flops, but otherwise we are still utilizing all the gates and combinational logic that we have learned before, right? So everything is still related, everything is still relevant. All right, so synchronous sequential circuits or synchronous counters in this case. So let me actually save that. All right, so in this case I'm trying to, let's say, come up with a 4 or modulo 15 counter like before. The only difference now is I would like to have it synchronous. That means each of my individual flip-flop is applied the master clock at the same time. So these are the enable inputs. So these are the J, K, let me call this J, D, KD, QD, JC, KC, QC, JB, KB, QB, JA, KA, QA. Now, I'm making it synchronous, and the way I'm doing that is by ensuring that each of my flip-flop is connected to the master clock. So everything is synchronized with the master clock. That's the master clock. Okay. All right. And this is the count I want to get. So this is 2, 3, 4, 5, 6. All right. So this is what I want to get. Let me do this. And so on until 15. All right. Now, let's examine each individual input or output independently and see what kind of a circuit modification I have to do to get that kind of a response. Okay. Let's examine QD to start with. QD, because that's the simplest one. Right? QD should toggle with each clock pulse. Right? That's exactly what is happening here. QD should toggle with each clock pulse, with each master clock pulse. With each active edge on the master clock, my QD has to toggle. So how should QD be configured as? Let me ask that. How should one configure QD to, I'm sorry, QD as in my this flip-flop, JD, KD flip-flop? How do I configure that so that I can get a QD that toggles with every active edge of the master clock? Of course, the master clock is applied directly to QD. So that's simple, I hope. Do you see that? What should I do for the first or for the JD, KD flip-flop to get that kind of a response? Because this is just this basically toggles with every clock pulse, I just have to configure this in the toggle state. I just put KD and JD and KD to be 1, and I can obtain the QD response. Okay. Okay. What about QC? How can I obtain QC? Kind of the QC response. What modification should I do in my circuit to get this QC response? Let's examine QC. So QC should be 0 on the 0th clock. Of course, it's 0 on the 0th clock pulse. Should remain 0 on the first clock pulse. On the second clock pulse, it has to toggle from 0 to 1. Okay. It should remain 1 for an additional clock pulse on the third clock pulse, and then it should toggle again on the fourth clock pulse. So basically, it should remain in a particular state for 2 clock pulses, toggle, remain in that toggle state for 2 clock pulses, toggle again. So basically, it has to exhibit this kind of a behavior. All right. Now, how would I obtain this? So I cannot really work with the clock anymore because clock is taken away. I'm applying the clocks. That's everything is now that's done. I cannot touch that anymore. The only thing I can touch is JC and KC inputs because they are not no longer. I mean, they are not touched yet. By the way, just for your reference, let me just put down the characteristic table for the JK flip flop here. JK QT plus 1. Okay, 0 0 0 1 1 0 1 1 0 0. Applied on J and K corresponds to the memory state, so QT remains as QT. So qt plus 1 is nothing but qt. So what was there before continues to remain in that form. 0, 1 was the set. I'm sorry, the reset state. 1, 0 was the set. 1, 1 was the toggle state. Q prime of t. Okay. All right. So that's the characteristic table for the JK flip-flop. Now, how would I obtain this? As you can see here, what if I apply QD, the output of this flip-flop, as the input to JC and KC? What's going to happen then? I'm applying QD as the input to JC and KC. So that means when QD is 0, I'm applying 0 and 0 to KC, JC and KC. J and K both zeros corresponds to the memory state, right? So when I apply 0 to Q, JC and KC, I'm placing this in the memory state, right? Placing this in the memory state. That means in the next clock pulse, my previous value of QC remains as 0. Right? In the next active edge, because I'm applying 0 on my JC and KC, in the next active edge, it's in the memory state, so it keeps the same value. Okay. Now, on the first clock pulse, I'm applying a 1 on QD. I'm getting an output of 1 on a QD, and I'm applying that to my JC and KC. 1 on JC and KC, 1, 1 corresponds to the toggle state, right? So in the next active edge, my output on QC should toggle, right? So 0 becomes 1. Now on the second clock pulse here, I'm applying a 0 on my QC, on my JC and QC. That means again, I'm taking it back to the memory state. That means in the next active edge, because I'm applying a 0 on JC and KC, in the next active edge, 1 remains as 1 because that's in the memory state. I'm configuring the JC and KC flip-flop in the memory state, so 1 remains as 1. Okay, and this continues. And then again, I'm toggling because my QD becomes 1, applying a 1 on my JC KC. So in the next active edge, my flip-flop again toggles. I'm changing the value of QD to be 0, applying on JC and KC. Next active edge, that remains in the memory state, and the process continues. So I get this kind of a response. How did I do that? I just applied QD to both JC and KC. All right. Now, what about QB? How do I get the response of QB? My QB has to be in the memory state. So let's talk in terms of memory state now. My QB has to be in the memory state for these number of clock cycles. Okay, and then it should toggle on the third clock pulse from 0 to, so basically I have to be 0 for 4 clock pulses, toggle on the 4th clock pulse, and remain 1 for 4 clock pulses, toggle on the 5th clock pulse, and so on. Right. How do I get this response now for JB and KB? What should I do? What should I apply? Again, the only thing I can apply to is on my JB and KB inputs, right? My clock is taken away. I cannot do anything with the clock. So the only thing I can do is on JB and KB. What can I do? Do you see anything from the, could you observe? So for this, do you see anything from this truth table? Yeah, you need to look at the, I'm sorry, the table here that shows you the count. You need to look into that. Exactly what we have done for QD. Do you see any kind of a pattern here that we can use so that we can obtain that response? Let's examine it closely. It has to be in the memory state. Until this point, it has to toggle here. What is it I can do to make it toggle here? When is it toggling? If you notice the QC and QD input outputs, it has to toggle when my QC and QD both become 1. When both becomes 1, in the next clock pulse, in the next active edge, my QB should toggle. So I need to test somehow that when it becomes 1, when QC and QD are 1, right? Until they both become 1, that should be in the memory state. But once they both become 1, in the next active edge, that should toggle. I hope you got the clue. So what I can do here is, I can basically take QD and QC, apply an AND gate here, and apply the output of the AND gate to both JP and KB. So what does this do? As long as the output here becomes 1, I'm applying a 0 on my JB and KB, 0 on my J and K, places that in the memory state. So the values remain. The moment it becomes 1, I'm applying a 1 on JB and KB. So in the next active edge, my output QB toggles. Okay. Now immediately my QC and QD values are again changed, right? So now, so basically I'm applying this back in the memory state. So these values remain. When do they toggle again? They toggle again when I apply JB and when my QC and QD become 1 again, both 1 at the same time. And in the next active edge, my QB toggles again from 0 to 1, from 1 to 0, and so on. So I got this response for QB. Okay, let me just make sure that we don't have these distractions. Okay. Now, what about JA? What about J and KA flip-flop? The response. Again, it has to be in the memory state until when? Until my QB, QC, and QD, they are all ones, right? When they're all ones, in the next active edge, my QA should toggle, right? And then it remains 1 until my QB, QC, and QD become 1 again, which happens where? Here somewhere, right? No, actually, no more. I mean, if we here, then my QA becomes 0, this becomes 0, this becomes 0, this becomes 0, and I basically I start counting back again. So it goes from 0 to 15, resets to 0, and then goes back from 0 to 15, and so on. Right? In other words, I have to apply QC, QB, and QD as inputs to J and KA. In other words, I can apply this with another AND gate here, apply this as the input to JA and KA, so that I can get this kind of a response for QA. Now, as you can see here, now that's synchronized with the master clock. The only propagation delays I have to worry about is through these individual gates, which is not going to be very significant. So I can actually construct a large counter using the synchronous counter method. Okay. Let me see if you have any questions on this. Any questions on this, on the synchronous counter? Does it make sense? How we worked around the constraints, examining the response and trying to come up with a circuit that would fit that response. Okay. Any questions, guys? Are you all good so far? Okay. So with that, in the next class, we're gonna again shift gears, and then we're going to look at a different design approach for the design of digital systems, a more generalized design approach, okay, for the design of digital systems. So until then, if you have any questions, just let me know. And yes, I'm going to post the lecture. I know the last lecture was kind of, I was not very satisfied with the quality of the last lecture. The recording quality was pretty bad. Let me do something about that.